me share the screen. So I had started discussion on ARM assembly language. Some instructions we have introduced, basic ones, which you can use to write some very elementary programs. So we will continue with that, introduce more instructions, and have a closer look at how the instructions are represented inside the machine. So there are a couple of questions we'll try to answer in this lecture. One is that there are some instructions which specify a constant, and these constants have a limitation on their size. There is a range in which the constants can vary. So there were questions about this actually, that how can an instruction specify a 32-bit number? So there's a limitation because each instruction is of size 32 bits, and obviously one of the key things in an instruction is the opcode, or what the instruction is going to do. So obviously there are not all the 32 bits left for specifying a number. We will see how in different instructions different limitations are there. Then the next thing we'll look at is, well, not necessarily in this order, that how do you deal with individual bits or bytes in a register? Okay. Then what happens if you have you make a comparison, and before branch you have some other instructions. So what is going to happen? Is the result of comparison still valid or not? Okay, then I mentioned about stack. So how do you actually work with stack? And then encoding of assembly language instructions to understand their representation in the machine. So we talk of instruction format. The representation of instruction in binary form is defined in terms of some formats, because an instruction has several parts, several things it has to specify, and each of these parts is called a field. Okay, so instruction has many fields, and arrangement of fields is called the instruction format. So there are multiple instruction formats where different fields are arranged in a different manner. So first let's look at the so-called DP instructions, or data processing instructions, like add, subtract. So consider instruction of this form. RD is assigned Rn plus some operand. Okay, that's the second operand. So RD is the destination register. Rn is the register specifying first operand, and second operand requires some detail. I'll come to that. So these are the four things we are trying to specify. One is that it's an add operation. Then second thing is destination register. Third is the first operand. Fourth is the second operand. The instruction has a format which is shown, so which has actually more than 4 fields. Okay, one would expect that you require 4 fields to specify these 4 things, but there are additional fields which are used firstly to place this instruction in the overall encoding scheme. Okay, so in particular, look at a field which I have designated as F. So F is a format type. It's a 2-bit field, which means it can have 4 different values, and one of the values specifies that it's a DP instruction, or data processing instruction. There are many data processing instructions, and plus is one of them. So this field called, let me enable the laser pointer. This field called OPC is the opcode. So this will tell that it's a register. Sorry, it's an addition operation. Okay. I'll talk of there are fields COND, I, and S. I'll talk of those later. But let's look at these three: Rn, Rd, and operand 2, which are quite obvious. So apart from this OPC telling it's an addition, we are specifying destination in RD field. Rn is the first operand, and for second operand we have, you can see it gives an impression that you have uh, many more things to specify, so it's a longer field. Okay. When you're writing assembly language, you don't really need to worry about this, but this the reason we are describing this is it gives you an insight into how instruction set is formed, how different instructions are represented. And in particular, this will be required when you design the processor, because processor has to pick up an instruction, look at various fields and interpret it. Okay. So we'll talk of details of operand 2. I'm showing values which are going into different fields. Sorry, these are the sizes of different fields. 4 bits, 2 bits, 1 bit, 4 bits again. So that means OPC can have 16 different possibilities. Okay. R and RD, these are registers. And since there are 16 registers, you need 4 bits to specify these. Operand 2 has 12 bits, so actually operand 2 can be a constant. It can be a register. So if it is a register, not necessary that all 12 bits will be utilized. But if it is a constant, you can see that there would be limitation in terms of the size. So if your instruction is add R1, R2, R3, that means R1 is the destination, R2 is the first operand, R3 is the second operand. Then what you will have here is okay. All right, I'll come to that in a moment. So here the second operand is a register, and that register number would be specified in this part of the operand 2 field. Okay, 8 bits are used for something else. Now, on the other hand, if the second operand is a constant 3, then it will be specified in 8 bits here. Okay, which means that this number could be whatever is limited by 8 bits. Okay, then 4 bits play a different role. And distinction between whether we have this form specifying register or an immediate is actually taken care by the I field. So I stands for immediate, and a format of this kind, specification of an operand in this manner, is called immediate, in the sense that the operand value is immediately available within the instruction. Okay. In the other case, the operand is coming from a register, but here operand is part of the instruction and it's called an immediate operand. So I specifies whether the second operand is going to be a register. I0 means that, and I equal to 1 means that it's going to be a constant. Okay, now as far as F field is concerned, I mentioned that for different groups of instruction there are different formats. So F equal to 00, it's a 2-bit field. It specifies that it's a DP instruction. All right. Now, I'm also indicating what is the role played by the remaining 8 bits if second operand is a register, or remaining 4 bits if the second operand is an immediate. So this specifies these 8 bits specify shift. That means register R3 or whatever is the second operand can be the operand could be obtained by shifting that register by a certain amount. Okay, how you shift, I'll talk of that shortly. But instead of directly using register, it is possible to shift it. So, for example, if you want to add 4 times the register, the shift could be used to specify 2-bit left shift, because shifting left amounts to multiplication by a power of 2. Shifting right amounts to dividing by a power of 2. So, in fact, you could say RD is assigned Rn plus another register shifted left or right by certain amount. Okay. In case of immediate operand, you can specify a certain amount of rotation. Okay. I'll describe these shortly. So first of all, there are 4 types of shifts. Logical shift left and logical
Excuse
shift.
me, sir.
Yeah.
So could you please explain what about S and OPC?
What about S
S
and
and OPC.
yeah. Okay.
OPC, this.
S I have not defined yet. We'll do that later.
Okay.
OPC is short for opcode or operation code. So OPC tells there are 16 DP instructions: add, subtract, reverse subtract, their carry version, and some more. Okay, all these come in the category of DP instruction following same format. So the field F, when it is 00, it specifies that we are talking of a DP instruction, and OPC 4-bit field will specify one of the 16 DP instructions. Okay.
Sir,
Yeah.
so like we are discussing the format of how the instructions we write in assembly will look in machine code, right? Like bitrep.
Yeah.
So like the assembler will transform our instructions to binary notation in this format.
Exactly.
Okay, sir. Thank you.
Yeah.
So then what does the first column do? Like if OPC is the OP code?
First column means, are you talking of first field?
Yes,
Or
sir, yes, please.
yeah, this is I had labeled this as COND, which stands for condition. So we'll talk of that later. Okay.
Okay, fine.
Okay. So let's look at these 4 different types of shifts. Logical shift left, logical shift right, arithmetic shift right, and rotate right. Okay. So shifting left or right, I think that you understand. The question is, what is the difference between logical shift and arithmetic shift? In arithmetic shift, as you shift right, the bit position which are falling vacant are filled with the sign bit. So you interpret the number being shifted as a 2's complement number with the leftmost bit indicating the sign. All right. So as you shift to give the effect of division by 2, or at least approximate division by integer division by 2, you want to maintain the sign, and therefore sign bit is replicated in the vacant positions. In logical shift, the vacant positions are filled with zeros. Okay. Rotate is just a circular shift where the bits which are going out actually are filled into the other side. So let me illustrate these pictorially. There are two things to be done. One is to specify which type of shift it is, and the second part is the amount by which you want to shift. Okay, so 5 bits are used for that. You can specify any amount of shift, but from 0 to 31 in 5 bits. All right.
Sir.
Yeah.
Sir, in arithmetic shift, are we maintaining the sign kind of thing?
Yes. In arithmetic
And,
shift, the sign is maintained actually.
and in the other two, LSR and LSL, we're not maintaining the shift because I mean.
Yeah, you are filling in with zeros.
Okay,
So
sir.
I'll
Thank
show a picture illustrate these in a moment. Okay. So I was talking of shift amount. You could specify shift amount as a 5-bit unsigned constant ranging from 0 to 31 or 4-bit register number. So that means the amount by which you need to shift need not be a constant. It could be a value coming from register. Okay. Of course, register would be 32 bits, and making a shift more than 32 doesn't make sense. So basically, when you are using a register to specify shift amount, only the rightmost 5 bits are relevant. Okay, inside the register, 5 bits are relevant, others get ignored. So how do you specify the shift in assembly form? Yeah.
When we do shift, so shift will done on result or on operand.
So, sorry, I didn't understand. Can you repeat the question?
Shift operation will be done on the result.
No, operation is not done on the result. This operation is done on the operand. If you want to do the shift operation on the result, so suppose you performed an addition without any shift. You added A and B. Okay. Now you want to shift the result. So you can use a move instruction. Move instruction like add instruction. Let me just. So move instruction would basically be move operand 2 to RD. Okay. So operand with operand 2 you can specify shift. And if you want the result to be remaining in the same register, the register specified as RM and RD could be same. So in fact, if you look at this RN, RD, RM, they could all be distinct. Some of them could be same, some could be different. So all combinations are allowed. Okay, they all don't have to be distinct. And as I mentioned here, that shift amount could be specified by a register. So this is a 4th register coming into picture. Okay. So you have RD, you have RN, you have RM, and then you have a register specifying the shift amount. So 4 registers could be involved. Now, how do you write this in assembly form is also shown here. For example, the operand 2 could be RM, the register which you want to use as operand, comma, the shift type and the shift amount. Okay. So in terms of format, you recall that we had left 8 bits to specify shift. Okay, RM is the second operand, and this whole thing is a 12-bit operand 2 field, which is subdivided into 4-bit for specifying RM, 5-bit. This 2 bits are for shift type. Okay, so whether it is LSL or rotation or arithmetic shift, one of those 4 could be specified in these 2 bits. And a 5-bit constant is sitting here. In this example, we are specifying this constant as number 4. Okay, so you are trying to shift it left by 4 bits. And we are left with 1 bit here, okay, 5 plus 2 plus 4, that is 11, and the 12th bit is kept 0. Here we are specifying the shift amount by a register. Okay. So instead of 5-bit constant, we have a 4-bit register. Okay. Sorry, 4-bit register field to specify one of the registers. Again, 2 bits are for shift type, and this bit is put 1. So this is the bit which distinguishes whether shift amount is a constant or coming from a register. Okay. So in case of register, there is still 1 bit which is kept 0, and if you make this 1, it is used for a different type of instruction. In specific case, this you make it 1, it's used for multiply and some other instruction. So you might get a feeling that it's something very weird and clumsy, and in fact it is. Okay, so rest of it could be like a DP instruction, but if you make this bit 1, it becomes a different format. So it's a little awkward way of defining instruction, but this is what happens when you try to pack too many instructions in limited number of bits. Okay, shift type. These are the 4 codes for 4 types of shifts, and that's very straightforward. Any question here?
Sir? So the RS that we are specifying in the second case, so sir, is the value stored inside the RS defining how much shift is required?
Yes, yeah, right. The contents of register RS define the amount of shift you want to do.
Okay, sir. Okay.
Any other question?
Sir, you have different kind of DP instructions such as multiply or addition, but
Yeah,
like multiplication and addition take different amount of time in a circuit.
just let me interrupt you. Multiply is actually, although it's an arithmetic instruction, it is kept in a different category. So in DP, among DP instructions, we have add, subtract, move, compare. All these come in DP. So I'll show you a full list in due course of time.
Okay, sir. So anyways, like multiplication will take like in a circuit more time than an addition. So isn't there a huge overhead between that if you move a simple addition or a multiplication?
It's an implementation issue. Yes, typically multiplication is a more complex operation, and it could take more time than addition. So when we discuss implementation or the processor design, we'll see how different instructions are implemented. So multiplication could take longer than addition. Yeah, so did I answer your question fully, or something is still left out? Let me know.
Yes, sir, it's answered.
Okay, so let me illustrate.
Excuse me, sir.
Yeah, please.
Sir, like when we store the shift as a constant, then we have got 5 bits. But when we store it in a register, we have got just 4 bits.
Yeah. Yeah. So yeah, what we are saying here is that the amount of, suppose you want to shift by 4 bits, 4 positions. Okay. You can specify the constant 4 within the instruction, or that number, the amount of shift could be stored in a register, and that register number you are specifying here. Okay, so suppose you want to use R10, register number 10, to specify the shift, and R10 contains the value 4. Okay, So
Okay, sir. Okay, sir.
you will specify 10, and whether you are specifying a register or a constant is decided by this particular bit.
Okay, so those 4 bits are for storing the address of the register where that shift is.
That's
stored.
right. That's right.
Okay.
Yeah. So you can call it register number or register address. So basically, it is address of the register within the register file.
Sir, in this arithmetic shift right, it will multiply by 2 while maintaining the sign, right?
Shift right actually amounts to division by power of 2.
Oh, sorry. So for multiplication, we cannot multiply while maintaining the sign.
Okay, now multiplication. A related question is, why don't we have arithmetic shift left? All right, you have two kind of logical shift, left and right, but arithmetic shift we are talking of only shift right. So when you are multiplying by 2, there are two possibilities. Multiplying by 2 or any power of 2, there are two possibilities. The result is within the range of 32 bits or it is not within the range of 32 bits. So it might overflow. Okay. So that's a let's say that's a case where you cannot have the result contained within the 32 bits. Suppose there is no overflow, then logical shift left itself will preserve sign. Okay. Suppose you want to multiply by 8. Okay. Then you will try to do it by shifting left by 3 positions. If the number is if the result is within the range, left shift will not lose the sign. It will preserve the sign. If left shift causes change of sign, that means overflow has occurred. Okay, so therefore there is no separate need for arithmetic left shift. If you have to
Got it, sir.
perform,
So like when we are right shifting, if there was like a 1 in the most significant bit and we right shift, then it will like be replaced by a 1 only in arithmetic shift.
Yeah, we have 1 still sticking there. Okay, so logical shift left is illustrated here. Suppose you are shifting by 3 positions, then bit number 0 to 28 are going to come to the position 3 to 31, and on the right hand side you will introduce 3 zeros. Also, one additional thing is that the last bit which is getting lost, so basically 29, 30, 31 are getting lost, they are getting shifted out. Out of these 29 you could consider as the last bit which is going to be thrown, and that will be preserved in carry. So as a result of this instruction, carry flag would be set if this bit number 29 was 1. Carry flag would be reset or made 0 if bit number 29 was 0. Okay, this is logical right shift. So you have zeros coming in from the left side. Okay, and if this was a signed negative number, then you would have lost the sign. So that's why there is a need for arithmetic right shift separately. So here again the last bit which is going to be thrown away is preserved in carry flag. This is the arithmetic right shift. So suppose this was the sign bit. The bit number 31 is the sign bit S, and copies of this are filled in the vacating positions. This is rotate right. There is no rotate left because it's a circular thing. Right rotation by amount X is equivalent to left rotation by amount 32 minus X. Now, recall that when the second operand is a constant, I had divided into 2 parts. 8 part I said is immediate, it's a constant number, and 4 bits for rotation. So even the constant operand can be used with some rotation. All shifts are not available. It can be rotated by certain amount. It could be rotation by 0 or rotation by a number up to 15. Okay, so actually the number you specify in ROT field is 0 to 15, but rotation amount is actually twice that. So this 8-bit constant is first 0 extended to 32 bits. That means you take 24 zeros, make it a 32-bit number, and then rotate right by 2 times this number. Okay, so if you have specified 3 here, then you rotate right by 6 positions. So with this number varying from 0 to 15, the rotations that are possible are from 0 position up to 30 positions. So one use of this you can see is to, in absence of this rotation, you are limited to only specify constants from 0 to 255, which is fairly limited range. But this rotation makes it possible to specify larger constants. Okay. But not all possible large constants are possible can be specified. Limited ones can be described in this manner. So for example, suppose you want to specify 400 as the operand. Now this is beyond 255, so you can't specify in 8 bits. But if you take if you put 100 in immediate field and say rotate right by 15, that means rotate right by 30 positions, what will happen? So it is equivalent to left rotation by 2 positions or multiplication by 4. So you can specify 400, although it is a bigger constant. So is that clear?
Sir, how did 30 bits correspond to 2 positions?
Pardon? Oh, okay. This is rotation. It's a right rotation. So which is cyclic. So let's look at this. Sorry, here I think I shouldn't have put zeros here. It's these 3 bit number 0, 1, and 2 will come here. You're rotating right by 3 positions. So no bits are getting lost here. The bits are circulated rightwards. Okay, so all bits are retained.
Okay, sir, got it.
They get shifted. So rotation, right rotation by 3 bits can also be considered as left rotation by 29 bits. Right, so it comes to the same thing. You know, you rotate left by 29 bits, it will come to the same position as you'll get by rotating it right by 3 positions.
So
yeah,
would we still have a carry bit in case of rotation, since we aren't really losing any bit?
Yeah, so in that sense, what I said is not accurate, but you could say the bit which is in this position will go to carry. It's not getting lost in that sense. All right, because this will be sitting here. Okay, the old bit 0 is here, old bit 1 is here, old bit 2 is here. So it's not getting lost in that sense, but this is what goes to the carry.
Okay, sir. Thank you.
Okay, so just a little exercise for you. Suppose you want to specify 800, the constant 800. Okay, how will you get that?
Like we'll specify 50, and then in rotate we would have, I think so,
So 8.
8. No, not 8.
40.
You want you take 50 in the immediate field and you want to multiply it basically by 16. Okay, so multiplying by 16 means 4-bit left shift, which is equivalent to 28-bit right shift. Sorry, not shift, rotate. So which is equivalent to 28-bit right rotation. And therefore ROT field could contain half of that, which is 14. Okay, now notice here that if you put 100 in immediate field and think of multiplying it by 8, that will not be possible, because multiplication by 8 means shifting left by 3 positions, which is an odd number. So in this case, rotation is possible only by even positions. Okay, rotation is in this case by 2 times what is specified by ROT bits. Okay, so you rotate by 0 or 2 or 4 or 6, only even numbers are possible. So the constant operand you can specify is something which can be obtained by shifting an 8-bit number by, or sorry, rotating an 8-bit number by even number of positions. Okay, so for example, if in your assembly language you specify hash 800 as a constant, assembler will figure out what to put in immediate part and what to put in ROT part. So for some constant values it may be feasible, for some it may not be feasible. Okay, now I briefly mentioned about multiply instruction. So multiply instruction of this type, multiply R1, R2, R3, is specified in this manner. Okay, so here is that one position. Recall that if you look at this group of 4 bits, 1, 2, and 1, total of 4 bits. If you have a 1 here and a 0 here, that means you are following this format. But if you have a 1 and 1, then it becomes a multiply instruction. Okay. If you have a 0 here, then this position is part of the constant. It can be 0 or 1. But if it is 1, then for DP instruction, it has to be 0. Okay. So the multiply format you will see has 1001. So there is a 1 here, there is a 1 here. Other combinations are there for other instructions, but multiply is characterized by this. So now what is this fourth register doing here? So RD is the destination. Here I've put the actual value. RD is the destination. We wanted R1 as the destination. So 0001, that's the destination register. R2, RM is the first operand, which is R2 in this case, and this is 0010. RS is the second operand, which is R3, so use 0011 here. But there is a fourth register I have put here. It's used for multiply instruction, it is 0, but for there is another instruction, multiply accumulate, where this is used. Okay, so here I'm putting decimal values of various field. COND field I have still not discussed, so I'm just leaving it blank. Okay, and this is the S field, 1-bit field, that also I have not discussed, so leaving that also blank.
Sir, can you once again mark which were R1, R2, and R3?
Okay, so in this, basically what we are saying is RD is the destination, RM is the first operand, RS is the second operand. So it's a different format than add instruction, right? And there is a fourth register field which is not used for multiply instruction. It is used for a multiply accumulate instruction which combines addition and multiplication. So we'll talk of that later. But this instruction, multiply R1, R2, R3, will get coded like this. Okay, so F is still 0, I is 0, OPC is all zeros, and this is 1001, this is crucial, and register specified here in these three fields. So now these formats would look very tedious. You don't have to actually remember these, right? So I'm sure you'll be finding it hard to remember. You don't have to remember. You have to just get an overview of how things are encoded, and some, particularly this coding of multiply instruction, is somewhat awkward. So here is the second instruction which I just mentioned, multiply accumulate, and its assembly notation is MLA. 4 registers are specified, and the meaning is R1 gets R2 into R3 plus R4. Okay, so a single instruction does this operation. Such an instruction is very useful when you are finding, let's say you have dot product of two vectors. Okay, suppose there is one vector A1, A2, A3, A4, other B1, B2, B3, B4. So dot product means that A1, B1 plus A2, B2 plus A3, B3, and so on. So this instruction actually simplifies a sum of product computation of this form. Rn is that fourth register. Okay. The OPC part is different. For multiply, we had 0000. For multiply accumulate, we have 0001. This 1001 pattern means that multiply, accumulate, they are again part of a subgroup. RD is 1, RM is 2, RS is 3, and RN is 4. That's for this example. If these registers are different, you will accordingly fill up this differently. you notice that in multiply instruction, the second operand is a register. So there is no provision for having one of the operands as a constant. So if you want to do something of this nature, multiply one operand which is in a register with a constant, then you will have to first move that constant into a register and then use multiply instruction. So it has to be split into these two. Multiplying by a power of 2 is easily achieved by move instruction with left shift. So this is what somebody had asked, that if you want to shift the result or multiply the result by the power of 2, what do you do? So this is how you could do it. Move R1, R2, LSL 4 would shift R2 left by 4 position and then put in R1. So R2 remains unchanged. And 16 times R2 goes to R1. Okay.
Sir?
Yeah.
Sir, so in the logic here with power of 2, if you're doing a logical left shift, will it work for negative numbers as well?
Yes, it will work correctly if there is no overflow.
Okay.
If there is overflow, you will get wrong result. But instruction will do the job and move on. Okay, the next category is DT group of instruction. DT stands for data transfer. And this includes load and store. So you want to move data from somewhere in the memory to a register. So RD is the destination register, and memory has its address specified as a sum of two things. One is the base, other is the offset. So the base is a register, contents of a register, and the offset could be specified in various forms. Could be a constant, could be a register, right? So you have F, OPC, opcode. RN is this register, RD is the destination register, and you have a field for specifying the offset. The size of this is 12 bits, 4 bits for this, 4 bits for this, and it has 6 bits for opcode. Okay, unlike DP where you had 4 bits, here you have 6 bits. And F is 0, 1 for this. So the contents of F distinguish whether it is a DP instruction, data processing instruction, or DT instruction or something else, right? So first let's look at this offset part. Now it can be a plain and simple 12-bit unsigned constant, or it could be 4-bit register number and 8 bits of shift specification, which is same as what you do for DP instruction. All right, so you will specify a 4-bit register address, and 8 bits could be specifying one of the shifts and shift amount either as a constant or in a register. So, but unlike the constant part which we saw in DP instruction, where you had 8 bits and 4 bits specifying rotation amount, here you have no rotation. Straight away you can specify a 12-bit offset. So here are some examples of DT instruction. You could write LDR, a destination register, and the address specified by base in R5 and a constant offset. So 32 is sitting in this operand field. F part is 0, 1, or in decimal I'm just putting a 1 here. OPC for this is 25. This is the destination, and that is the base. So here I'm showing example of indexing an array. So you have R2, which is holding the base of the array, the starting point of the array, and R5 is the index. So you multiply index by 4. As I mentioned earlier, you can't do this directly. This will require 2 instructions because multiplying by a constant requires loading that constant into a register and then multiplying. But in this case, since it is 4, you could actually do this by a shift operation. You don't need to use multiply instruction. So anyway, the attempt here is to take the index, multiply by 4, and add it to the base, and you get the address in register R2. Then R2 with no further offset can be used to address memory and load the data into R6. You can have that, if you want to do that using shift, that shift can be incorporated within the add instruction. So you are saying that add R2 and R5, where the second operand goes through a logical left shift by 2 positions. Okay, so you don't need a multiplication, you can do by shift. Even further, you can simplify things, that shifting and adding is part of the load instruction itself. As I had shown in the format, the second operand or the offset part, when it is specified as a register, it can be specified with a shift. Okay, so that's what we are trying to exploit here. So you're saying that load where R2 is the base, R5 is giving the offset, but along with a 2-bit left shift. So in a single instruction, you could do this array indexing. Now store is a instruction which is very similar to LDR. Opcode is 24. Here RD is not the destination, it is the source. And memory is the destination, not the source. But format is same, just the role is reversed. Now I talked of 6-bit opcode field in DT instruction. So that gives us many possibilities. We have nothing else but load and store, but it comes with many other enhancements, many other features. So these 6 bits of opcode are designated as I, P, U, P, W, L. There are names for these, and I'll elaborate on these. I stand for immediate. Whether the offset is being specified as a constant or specifying using a register with possible shift. P specifies whether you are using pre-indexing or post-indexing. The difference is that the addition which is being done, addition of base and the offset which is being done, is it done before accessing memory or after accessing memory. So pre-indexing means that the addition is done for address computation and then memory is accessed. Post-indexing is done. Post-indexing means that you use just the base as the address and then modify it by the offset and store in the base. So base is changed. Okay, base is updated for next use. U indicates whether the offset is to be added or subtracted. The offset itself is always positive. Suppose you're specifying a constant, you're specifying an unsigned constant. But by suitable choice of this bit, you can achieve addition or subtraction. Okay, so that offset could be added or subtracted. Bit B indicates whether you are talking of loading and storing of one byte or entire word. Okay, so although at assembly level, these may appear as different instruction. LDRB and STRB are load store bytes, but in terms of format, they are all unified. Okay, it is just this bit which distinguishes LDR from LDRB and STR from STRB. Bit W stands for write back, whether to write back address into the base register or not. So base plus offset is being done, and whether to leave the base register unchanged or update it with this address to write back this computed address into the base register. So W specifies whether that is to be done or not. So you can imagine that if you're doing post indexing but not writing back, it doesn't make sense. So post indexing makes sense only when you are writing back. Okay, otherwise you access memory without base plus address computation, and you're doing this addition afterwards. If you don't store it back, there is no use for it. L bit indicates whether it is load or store. So you could see that I talked about opcode 24 for store and 25 for load. So they differ basically in this bit position, which is the L bit. So 6-bit opcode, each bit has a specific role to play, as you can see here. And with this, there are lots of variations which are possible. Okay, the offset is immediate or not immediate, whether it is pre-indexed or post-indexed, whether the offset is added or not added, the transfer is a byte or a word, the computed address is written back or not written back, and is the data transfer from memory to register or register to memory. So all these things are part of the opcode specification.
So
yeah.
So in the previous lecture, we mentioned loading a half word. So how is that specified under the constraint?
That is a different instruction.
Okay.
That is not part of the group. So load half word is a separate instruction.
Yeah. So can you explain pre or post indexing again?
Yes, pre and post. So by indexing, we are referring to here as addition of the offset to the base. Okay, so you're adding a base and an offset. Whether this is to be done before memory access or after memory access. Pre-indexing means that first you perform this address arithmetic and then access memory. Post-indexing means that you first access memory and then perform this address arithmetic. Obviously, post-indexing would make sense if this address arithmetic is done and the result is stored back in the register. Otherwise, it is wasteful. You're not achieving anything. So, okay, now let's look at pre-indexing. If you are accessing arrays of an elements of an array sequentially, then with pre-indexing and a write back, you can actually do it very easily. So you don't need to keep on adding um, 4 to the address. Okay, so suppose you are accessing sequential words, then the address keeps on incrementing by 4, and that incrementing can be built within this load instruction by having indexing, let's say pre-indexing, and then write back. Okay, so index register or this offset register, the base register keeps getting modified, and you can access sequentially.
Excuse me, sir.
Yeah.
So, for example, LDR and SDR, they denote capital L, the bit L, right? So, what is the instruction that denotes P in the machine language?
Yeah. Well, in the machine language, it is by specifying these as ones or zeros. I think what you mean is how do you write these things in assembly? So that's the example I'm going to show.
Yes, sir.
So if you write LDR R4, R5, and with the offset part you put a minus sign. It could be a register, it could be a constant. If you put a minus sign, then the assembler will encode this instruction, putting a suitable value in U field. Okay, that up-down field, it will take care that it is a subtraction of the offset. Okay, so this is how you specify whether offset is to be added or subtracted. And with the offset part, you can specify a shift in the usual manner that is possible. This exclamation is specifying the write back. Okay, and you will write, suppose you wanted to use byte transfer only. So you'll do LDRB, okay, with some base, some offset, and this exclamation means that the computed address would be written back in R5. So R5 will get incremented by this amount every time you execute this instruction.
And sir, what about R4? Would that also be getting incremented?
No, R4 is not incremented. In R4, you're loading from memory with address specified in R5 and 32 offset. Okay, so suppose you were simply looping around this instruction. Next time, R5 would have been incremented by 32 already, and you'll add another offset 32, make memory access, put the result in R4.
Okay.
So, like once we pass this command LDRB, this exclamation mark. So the something is loaded in R4. Then when does like written back in R5 memory?
This instruction
After the operation
will modify two things. One is contents of R4 will be modified by contents which are brought from memory, and R5 will be modified by adding 32 to its old contents. So this instruction updates two things, two registers.
Then what is the use of exclamation mark? It was also done by LDR, right?
No. If this exclamation mark is not there, then R4, this instruction will not change R5.
Oh, okay, fine.
The addition is done only for the purpose of getting the memory address, but that sum is not stored anywhere.
Fine,
Sum is
okay.
used to access memory, but not stored in R5. If you put exclamation mark, it is stored in R5. And this will mean that W bit in the opcode is made 1. So next is straightforward. Okay. How do you write instruction with postfix, post indexing? There, if you specify this offset outside the square bracket, this indicates post indexing. So in particular, what this instruction means is that the contents of R5 form the address from where you get one word of data put in R4. After memory access, you add contents of R6 to R5. So R5 is getting updated after memory access. And that will be useful when you are using R5 next. So either within this instruction or some other instruction, R5 would have been incremented by then. Okay, so now look at this complicated looking store instruction. Once again, there is post indexing because the offset part is outside, and offset part is also getting shifted by 2 positions. Okay, before R6 is added to R5, R6 is shifted. I mean, contents of R6 shifted by 2 positions are added to R5. R6 is not changing. R5 would change. Okay, so now these load store instruction, I'll illustrate next how to use these for stack. So suppose this is your memory part of the memory, and the increasing addresses are in this direction. Okay, P is indicating top of the stack. So you may have different convention. This may be pointing to the last filled location, or you may say that P points to the next free location, empty location. So this is a stack. That means when you push something into this, it comes here and P moves to that position. Or in this case, when you push, the data is written here and P moves up. So when you push, the address should decrement. Okay, whether it is this case or that case, because this is the direction of increasing addresses. You could change. You could use a different convention. That I'm using a convention that stack grows in the direction of decreasing addresses. Okay, but one could do it otherwise also. Most commonly, this is how it is done. Stack grows into the direction of decreasing addresses. So a push would mean that address decrements, and pop would mean that address increments. First, let's look at the figure on the left. So in push, you will use pre-decrement. Okay, you will use store with pre-decrement because first you want to get this address of the free location where you want to store the new value. Okay, so it is case of pre-decrement. But when you want to pop, you will first memory access and then increment the pointer. Okay, so with this convention, you will use pre-decrement for push, post-increment for pop. In this case, when the pointer is pointing to the first empty location, you use post decrement for push. Okay, because first you fill up the location and then decrement. And pre-increment for pop. So first you make it point to the filled location and then read, and that becomes now the first empty location. So this is where you will use auto increment decrement and make a choice of pre or post depending upon the convention you are following. If your stack was growing in the other direction, then of course you can suitably change this. But with this convention, this is what you will do. So is that clear? Okay. Okay. That is all I have. Yeah, we have time for questions.
So why is this adopted as the convention that the stack grows in the decreasing addresses direction? Because that would not be scalable, right?
Yeah, I think it's the reasons are probably historical. So typically there are two memory areas used in a high level program. One is heap, one is stack. Okay. Heap will grow in one direction and stack will grow in the other direction, so that you get the storage utilized in a much better manner. So imagine that you have limited space where you want to keep these two structures. Okay. So one you start growing from one end, other you start growing from the other end, because you don't know which one will be how big at the runtime. So that's one reason, but I think there is no inherent advantage or disadvantage of one approach over the other.
Okay, sir, got it.
Any other question?
So can
Okay,
you show the previous slide once?
This one?
Yeah, so in this, like in the second last line, LDR, like when we have post operation.
Yeah.
So in this, the value of register, the value in at location R5 will be stored in R4, and then R5 will be updated, right?
Exactly.
Yeah, okay, sir.
Hello, sir.
Yeah.
Sir, you said that the content of R5 gets incremented by 32 and stored in there. So, sir, content, are we referring to the some address being stored in the registers?
Yes. So registers can contain data, registers can contain address.
So, sir, when we are saying that this hash 32 plus 32 in R5, so are we telling that the content is some address and that is getting incremented with 32, or any other
Exactly.
data can also be incremented with 32 or something like that?
Yeah. So if you look at this, for example, LDRB R4 R5 hash 32. So R5 has some address. To that address, we are adding 32 and getting a new address. From that memory, from this new address, we load a byte into R4. And also because of this exclamation mark, the new address is also put back in R5.
Okay, sir.
All right. So
Sir,
before,
uh,
yeah, you have a question? Yeah, sure.
sir, you say that the two stacks they are represented in different ways in ARM language.
Okay, I think let me let me postpone that discussion. I think okay, when I describe recursive function calls, probably I'll take it up again. Okay, so that's where we extensively use stack, and I'll touch upon this point once again there. Okay, thank you. Close now. I would again